Tromsø, Norway. Great. He will talk about relative differential invariants. So please, Boris.
Just a second. Let me choose the correct. Nice. Can you see my slides?
Yes, I can.
Just a second. Is it okay now? Do you see it well?
I do.
Fine. Okay, so I'd like to talk about relative invariance as joint or partially joint work with Sabin Schneider. Okay, so let me start. So the setup is that I have some Lie pseudo group, which means a continuous pseudo group consisting of local diffeomorphism given by a Lie equation, right? So it's determined by some manifolds in some jet order. So you can, in principle, think also about setup of groupoids, but it's better for me to think about actual Lie pseudo group in this case. So it acts on the manifold. It's action taken from prolongation of the point of the manifold, but also it induces action on submanifolds. So I consider n submanifolds, so O dimension n, and the corresponding jets, well, finite or infinite order. And so,
Boris?
Yes.
Are you still on the first slide?
Oh, that's no, actually on the second. So should I just probably reshare?
Yeah.
Yeah, it's still the first one.
Sorry for this.
Avin is right. Okay.
Do you see now my?
Yeah, now it's another one, another slide.
Okay. And it moves, right?
It moves, yes.
Okay, thank you. Okay, so so submanifolds of jets, I will denote those submanifolds of dimension n in manifold m by j m comma n. So the last argument is dimension of submanifold. Now, in particular, Lie pseudo group can be identified as subset of equation in J infinity m cross m comma m, where m dimension of a manifold. And particular cases of this construction, of course, linear case, Lie group representations, and then symmetry of PDEs, and also gauge actions. So the one of the main problems I'd like to address is kind of equivalence problem when we would like to distinguish germs or jets of objects like submanifolds or geometric structures. And the particular cases leads to normal forms, so shape recognition, image recognition, and signature manifolds. Now, the main tool for this are differential invariants, and these are functions constant on the orbit of the action. So we will consider orbit on the action of jets of submanifolds. Structures are encoded in the same way. And then actually every function will depend only on finitely many arguments. So it's actually taken from finite jet order, and then we take a projective limit. So it will be considered also as functional and infinite jets in this way. So there is a method of moving frame by which is just elimination of parameters, and it's applicable in cases when the group action is explicit and actually free. So which is seldom case, but that's quite effective. If the group action is not given, but the algebra given instead, then it's actually more complicated to operate with this, but then there are some other methods to do. So some of them maybe Avin was talking on the seminars. What about the structure of the space of differential invariants? this is classically just locally. People consider it locally, or even what we call micro-locals, that's in open sets and jets, which can be non-G invariant. But recently, the global picture was constructed, and these are algebra field. Okay, so and with this picture, the more natural approach is to consider rational differential invariants. And they actually arise often in classification problems. And a careful look shows that all examples are such, but simultaneously one see many classical expressions with root. And here's one example of expression with root. So if you consider motion group or proper motion groups, also no reflection, so connected group, right? And then it acts on the curves in Euclidean space, right? The group acts on the plane, and therefore it also acts on the curves. And the classical curvature is this expression y double prime divided by 1 plus y prime square, and denominator in power 3 over 2. Okay. However, even though it's classically accepted, that's not an invariant of group of motion. Okay, so that's what is called curvature. Actually, is not an invariant of group of motion, because if you take reflection, change sign of x and y, then the circle is preserved, but the curvature of the circle changes sign. Okay, basically the under root expression changes, the root changes branch, becomes minus root with this. So that's actually a rotation by 180 degrees, right? So it's continuous transformation. So you continuously change your invariant, and then you get different signs. So K is not an invariant, but K square is a bona fide invariant, and it's rational. Okay, so that's kind of argument for why we have to consider actually rational invariants. Okay, so here's and then there's strict algebra of invariants, but there's specification. So we will go and consider algebra of invariant functions. They have to be invariant with respect to G first, and second, they have to have specific algebraic behavior. So here's letter L. There's A, L, right? And L is some jet order. And this algebra is filtered by order K jets also. So every function is defined on some K jet space. Okay, therefore we take the projective limit or union. Okay, what is this L? So L signifies that we consider functions which are smooth by base, rational by fibers of the jets, and actually even polynomial by jets starting from certain order. And that's up to certain order L, we allow rational behavior, but starting from this, only polynomial behavior. Now, so here is the structure theorem proven by Valentin Luchagin and me more than 5 years ago. So we call it global Lie-Tresse theorem, because the micro-local version of this was formulated by Lie-Tresse. So we consider algebraic action of pseudo group. So its pseudo group also should be algebraic. So which means given by algebraic equation. And so this action on formally integrable algebraic reducible differential equation, all manifold M, such that on the base, on J0, on the level of 0 jets, the action is transitive. Okay, so on the level of points, the action is transitive. On the level of jets, of course, there appear invariants. Now, the theorem describes invariance. So
sorry, Boris, when you say this algebraic, you mean that's algebraic on the jet fibers, right?
Yes. Mm-hmm. Well, actually, it doesn't matter on the base, because on the base.
Yes, right, because it's, right, the fibers are affine from a certain level, right? So,
yeah. So the base is transitive, so I don't specify, it's just smooth sections there. But in fibers, we have natural affine structure. And yes, this preserves the structure. Okay, so then there is this jet number L, and the risky closed invariant proper subset S, such that in the complement to it, so you see, I take this equation E. In principle, you can say there's no equation, it's just like the entire jet space. And I remove this subset S, or its pre-image. Okay, and that set is actually the risky open. Now, In this set, the action is regular, which means that it foliated by closed orbit. So I can do quotient, and that will be a good quotient, rational geometric quotient. Okay, and this means that there are invariants, some finite number of invariants from this algebra AL, and finite number of rational invariant derivations, okay, derivation of this algebra, such that any function from the algebra of invariant is a combination of those. That is, polynomial of differential invariants which are obtained from this initial basis I1 to IT by invariant derivations. Okay, coefficients of this polynomial can be rational functions only of those initial invariants. Okay, that's the only thing where rationality appears. So that's the only thing where we can have some division. Okay. Now, my talk will be about relative invariance. The previous story was about absolute differential invariance. I will talk about relative invariance. So, what those? So we consider Lie algebra sheaf of this pseudogroup G, also denoted by G. And let me first formulate the story on the manifold. So that's why I actually don't write any prolongation signs for jets. It's just like, let me say the story for manifold. Function R is a relative differential invariant if the action by pseudogroup preserve it up to multiplier. This lambda G is multiplied, depends on G, on element of pseudogroup. Equivalently, and here, if I'd like to say equivalently, I assume the group is connected, pseudogroup is connected. So Lie derivative of R along vector field from the algebra G is proportional to R. And this coefficient of proportionality depends, of course, on element of the algebra that's called weight. So what is this? Let me focus on the right-hand side, right? So it's equivalent I can describe for pseudogroup, but actually I would like to discuss about algebra. So this weight, right? So it's what? So it maps from Lie algebra G to functions on my manifold E. Okay, so in fact, everywhere later I will assume that it's continuous function. So because I would like to talk about kind of Gelfand-Fuks cohomology. So that's actually continuous function. If G is big, that's important, right? So G may be infinite dimensional. Of course, absolute differential invariants just correspond to weight equal to 0, weight W equal to 0, or equivalently multiply lambda equal to 1. Okay, so these are functional coefficients here, right? So we can multiply by function. Now, if you do multiplication or division of relative invariants, that adds or subtracts their weights. So this the set of weights, therefore, is a linear space. And because absolute invariants are rational hunches, we assume that relative invariants are polynomials. Okay, so now I specify this space of functions which we see in here. So it's not arbitrary space of functions, but I would like actually to consider them to be polynomials. Well, when I go to differential invariants, I actually assume the same story. So they are smooth by base and polynomials by jets. Okay, now if we have a relative invariant and we write R equal to 0, that's a G invariant submanifold. I actually consider mostly just in this talk a scalar relative invariant, therefore it's just hypersurface. Okay, and it must contain singular orbits if R is genuinely relative, right? Not rescaling of absolute invariant. Of course, if I take absolute invariant and rescale it, I get relative invariant, but its weight will be exact. We'll see soon. Okay. Otherwise around, so if we have invariant hypersurface for dimension 1, then it is given by a relative differential invariant. Here I have to be a bit more precise. So if I would like it to be scalar function, then this has to be this submain, like what the hypersurface has to have trivial normal bundle. But if bundle is normal to is non-trivial, then it just means that I don't consider functions, but consider section of line bundles. Okay, so yeah, I mentioned here at the end that there is something about order of codimension k, but it's actually a more complicated story. I would like to skip it. So let's consider an example. So here's projective action on the plane. Okay, I take the group PSL3 and I act on the plane R2 with coordinate x and u. Well, in fact, of course, the PSL3 group doesn't act on R2, right? It acts on P2. So if you would like to say act on R2, then actually I assume it's pseudo group, right? Because it's just local actions. This is just things are just locally defined there. So I identify this plane R2 with space of 0 Gs of map from R to R. And the first R coordinate will be X and the second R coordinate will be U. So now I prolong this J0 to the jet space JK, right? Coordinates are going to be X, U0, U1, and up to UK. That's jet coordinates on the space. And the action is prolonged. And I write the corresponding Lie algebra, right? It's well, 8-dimensional, right? And for Lie algebra, the action is well defined. It's of course incomplete vector field over there, but it doesn't matter. So here's the all 8 vector field. You see 2 zero order, 2 or 4 linear, and 2 quadratic inversions. Okay, and here are the first relative invariants. Now, if you look to J2, there's just second derivative of U, and its vanishing is transparent, right? So when we write U2 equal to 0, this corresponds to line in the plane. And of course, lines are preserved by projective action. If you look to J5, right, it's a bit more complicated expression, but it's classical expression called Klein invariant. And its vanishing corresponds to quadrics. Okay, quadrics in the plane are given by J5 equal to 0, and indeed also this class of curves is invariant with respect to projective action. J7 is a bit more complicated invariant. Okay, however, the weight, so these are all relative invariants, they have weight, right? So which means they these weights W are elements from G star dual to this Lie algebra, which we see here, tensor functions on the space of jets, polynomial functions, actually. They will not depend on J0 in this case. And then actually weights for J5 and J7 are proportional. In fact, the weight lattice here is 2-dimensional. Namely, it's generated by the following two weights. And that's an interesting formula. It will reappear later, right? So here, X is fine-dimensional algebra. And of course, I can just take a basis, for example, the one which we see in here. And then G star is also split. Well, I can just consider basis of G star, dual basis. And so I will have to specify for each element of the basis corresponding polynomial. But instead, I consider X as a vector field, right? So these are vector fields on J0. And I will need to actually prolong them to fields on J1, J2, and higher. Actually, to compute those weights, it's just enough for me to have first prolongation. Well, first weight is actually determined by no prolongation at all. Take vector field from this algebra, general vector field, and I computed divergence on the plane with respect to the area form, dx du. Okay, that's actually mapped from Lie algebra to functions. So that's the first weight. To compute second weight, I do the following. I prolong these vector fields to first jet space, and first jet space is contact, right? And on contact space, I have contact form alpha, here it is. So I take actually volume 4 corresponding to alpha, and then I compute divergence with respect to this. So X becomes vector field in 3-dimensional space alpha HD alpha is volume forming this three-dimensional space, and W2 is corresponding divergence. So these two form a basis of weight lattice. Okay, and then from those relative invariants, we can get actually all absolute differential invariants. Here they are. The algebra will be actually A5. So the only division is possible by jets by expressions of jet order 5. Okay, everything starting from jet order 6 will be polynomial.
Sorry, but is U the same as U0?
U the same as U0, right?
Okay.
Yeah. Yeah, sometimes, yeah, like in this algebra, U is the same as U0. Yes, when I because that's non-prolonged, right? And then when I do prolongation, I already have to indicate the jet order. That's why I put 0. Mm-hmm.
I have a question. That is a kind of.
Can you speak a bit louder? I don't hear you.
So okay, that is my. Can you hear me now?
It's pretty weak. Pretty weak.
Okay, so yes. Next time I should change another audio output. One thing is very okay. So I should speak very loudly. I remember that I just want to understand the motivation of relative invariant. And as I remember the time it was in Moscow, yeah. Then Weinberg already introduced the notion. I mean, not Weinberg, but it used a relative invariant to produce integrable system, right? Hamiltonian system on Lie algebra. Do you remember? You must remember. So,
I mean, of course, relative invariant appear also in those contexts as well, right? So this is absolute classical objects. Yes, yeah. I mean.
So there are some relations. That's how you come to this definition. That means that there are relation between classical notion of relative invariant and these. Right.
I mean, there's lots of relation. I mentioned some at the end, but of course, it's very classical notion. Actually, the first paper on relative invariance was written by Alfvén in mid-19th century.
Okay.
Yes, of course. Yes, it has relation. And the algebra of all absolute differential invariants is generated by one invariant function. I'll call it I7. That's typo here. That has to be J7 cube divided by J5 power 8. And you see that power 3 and power 8 are precisely that's 3 to 8 is ratio of weights for J5 and J7. So I take the corresponding power, so the weights become equal. And then when I divide, the weight subtract, and I get actually weight 0. That is absolute invariant. So that's this I7. And then I also need invariant derivation. So I form it from dx, total derivative by x, by multiplying by certain invariant. Well, that has relative invariant actually as a factor which is there, but nabla then becomes absolute. Okay, so that's one example. Now let's discuss the condition of relative invariance.
If I understand correctly, geometrically you classified curves in P2, right? But it's easier to work on the affine part because otherwise
it's a fine chart, right? You're absolutely right. So it's curves in P2 with respect to projective action, but that's just a fine chart.
It's hard to work with projective coordinates.
No, I need coordinates, right? I would like to write some expressions, but that's the global picture, of course. Yes. Yeah, you're right. So now let's write consistency condition. So commutator of Lie derivatives is equal to Lie derivative of commutator. Apply this relation to R. And then we get one cocycle condition for the weight. Okay, so weight has to satisfy this relation, which is clearly just one cocycle relation. If you see these G star tensor functions map into wedge 2 G star tensor functions, right? That's just Chevalier-Eilenberg differential. But we consider continuous topology, so that's actually become rather Gelfand-Fuks differential. But now just so W is a one cocycle, right? However, what happens if I change R? I can change R by multiplying it by non-zero function here. So then, of course, it's still relative invariant. However, weight will shift. So weight W will shift by d logarithm f. Okay, so this is coboundary. So we have that W actually are one cocycles modulo one coboundary, and this identifies with elements in Gelfand-Fuks cohomology, H1G, functions, and functions well specification, as I said. Of course, in this case, both G and this PE, which are polynomials on E, well, can be infinite dimensional. In particular cases, Lie-Reinhardt algebra. So when actually G is also modulo over P. So suppose we have already computed this, and we have this cohomology. Then that's still not enough. One have to check realizability condition for cocycles. Which weight defined the relative invariants are? Okay, because maybe for some cocycles there's no R. And then this actually yield the space W, space of weights. Now, when we go to differential invariants versus just relative invariants, then two additional conditions arise due to local algebraic property of the pseudogroup. So the cocycles should be local. That is determined by finite jets, right? So they shall be determined by a finite number of derivatives, so of whatever field you have. Second, when we talk about base G0, the things are smooth here, there, and that's enough just to require that f is non-zero smooth function, because this cocycle is also kind of, this exact one cocycle is also smooth. However, when we talk about higher jets, I would like to preserve polynomial behavior, okay? And then f have to preserve this, right? And d log f is no longer a polynomial. So if f is just a polynomial, so that's actually one have to take very careful well, exact cocycles.
Sorry, Boris, again. So when you say local, you mean that it depends on jets and then integrated on. So it's derived via the horizontal context, right?
Yes.
Okay, so it's more like Chevalier-Lindbergh for the algebraists rather than Gelfand-Fuks, if I understand correctly. Mm-hmm. Because it's defined on the jets of your pseudogroup.
It's defined. Well, but there's also formal story in Gelfand-Fuks, right?
Yeah, it's some kind of subcomplex of Gelfand-Fuks. Right?
Yes. I just like to say that's well, continuous cohomology. That's also a possibility.
I think once you call this something like diagonal complex or something of that sort, if I remember correct. Is it correct? Anyway.
No, I mean, yeah, it's just if you want Chevalier-Lindbergh continuous cohomology, yes. But yeah, I would a bit be careful with calling it algebraic because it's a bit more general story there. So I don't know how all the things will work in an algebraic context. Okay, so now let's talk about interpretation of this. So I still talk about manifold, and then we will generalize to jets. So G is just a pseudogroup, or Lie algebra vector field, or Lie algebra sheaf. F is functions on the manifold. Or actually, we can do specification, but I say for algebra functions, polynomial. Yeah. Then elements of this cohomology gives lists of vector fields from vector fields on M to vector fields on M hat. So I will denote the Lie algebra G hat. It's abstractly isomorphic to G, where M hat is total space of line bundle over M. Okay, in the simplest case, when I talk about functions, that's trivial line bundle, but this can be generalized to any line bundle. Now, so in the trivial case or in non-trivial case, when I just use local coordinate t on the line bundle, this lift is the following. So x hat is equal to x plus the weight evaluated on x times dt. Okay, and then if you write the homomorphism condition x goes to x hat with isomorphism of the algebras, then actually you will see W has to be one cocycle. And changing section in this line bundle, you will see you can change it by coboundary. Now, there was work by Mark Fels and Peter Olver in 1997, where they in particular proved that for a weight W, there corresponds a relative invariant R if and only if the lift G hat possess new absolute invariant in M hat. So of course, if you have invariants in M, you can pull them back in M hat. But then the statement is that relative invariants in M arise if and only if you get a new absolute invariant in M hat. That's a bit rephrasing of Fels-Olver. They don't state it like this over there. Okay, so relative invariants are in bijective correspondence with invariant sections of the line bundles. And zero loci of those sections, or in other words, divisors, correspond to invariant hypersurfaces. This relative invariant equal to 0. Okay, there are more lifts than just those lifts which I described above. Those which I described above are constant in T. So you see that this factor of del T, it doesn't depend on T at all. It depends on the coordinate X of the manifold M. Equivalently, you can actually change this del T to T del T by log transformation. And then this lifts will be just linear lifts, right? So you will respect linear structure in this bundle. But there are non-linear lifts, okay? So for instance, they can be affine lifts where the factor will consist of 0 and first order terms in T, and also projective lifts where the fibers will consist of 0 first and second order terms in T. Okay. In fact, for finite dimensional Lie groups, these are all lifts, and this appeared in well, it goes back to Sophus Lie and was explored in a PhD thesis by Eivind Schneider. Okay, so now that's maybe main theorem. Under the same assumptions as global Lie-Tresse theorem, algebraicity, reducible, transitive on the base, the space of weights is a finite dimensional lattice, right? So finite dimensional one thing, lattice is the other thing, right? It's discrete subgroup of a linear of abelian group, which is vector space. Then there's this jet order L such that every relative invariance of order K greater than L and weight W is a combination of absolute differential invariance with coefficients being weights W relative invariance of order not greater than L. Now, the graded algebra of polynomial square relative invariance is just this R sum of RW. Okay, so where W runs by weights. So it's finitely generated by finite number of differential invariants and invariant derivations, very similar to the previous. It's just that here we have more polynomial behavior. You have to consider this R as actually graded algebra. Sum of two relative invariants, it's in general not a relative invariant. If you sum relative invariants of different weights, it is not a relative invariant at all. However, of course, every RW is just a linear space. So then you can do sum. And also product of RW1 and RW2 will be relative invariant of weight to W1 plus W2. Okay, so that's just graded algebra. Now, finite generation above should be understood not in the sense of Hilbert-Basis theorem, but via localizations on subset of invariants of order up to L. So equivalent, you should allow to divide by lower order relative invariants. Okay, so let me give you one more example. This is a small part from an ongoing group with Eivind. So we consider the following algebra G of vector fields. There are 6 of them. And this is subalgebra in symplectic algebra, SP4R. Equivalently, you consider the contact space J1 mapped from R to R. Okay, that's three-dimensional space. It has coordinate X, Y, and Y1. Okay, so here I don't actually write Y0, I just keep Y here, but I keep Y1 for first jet coordinate. And in this space, X, Y, and Y1, you have maximal subalgebra of algebra of contact vector field. That's 10-dimensional algebra. It is isomorphic to SP4R. And then in this algebra, right, so that's in abstract notations called C2, you can take Borel subalgebra. There's parabolic subalgebra P12. It's 6-dimensional. Here you see it as vector fields. Okay, so now we consider relative invariants of this algebra. And here is the first. Index below denote order, right? So if you go previously, this RWC, it's index above, superscript, that's weight. Index below will be order of invariant. So it's 3. So first relative invariant arises in order 3. It's just y3, triple derivative. Then more complicated invariants in order 6. Sorry, in order 5, and then order 6, 7, 8, and so forth. So we'll get 1 new relative invariant in each order. Weight lattice will be just 1-dimensional here. So it corresponds to line bundle of contact forms, right? So J1 is contact manifold, but there's no canonical contact form. So you just consider the bundles of all possible forms, that's line bundles, there's corresponding weight associated to it, right? Or in other words, I take vector field X, I differentiate contact form, it's something proportional to contact form, I divide by it. I take this coefficient of proportionality actually with minus, it's more convenient. Oh, sorry. Shit, that's not contact form. No, actually, yes, I'm sorry, that's just dx. Alpha is just dx here. Yeah. Okay, so the meaning of this weight is the following. So if you look to x5 actually, 1, 2, 3, 4, here's x5. X minus x dx plus y1 dy1. So if we prolong it, it will be the vector field of the following form: minus x dx plus summation from 0 to infinity n yn dyn. Okay, and then this actually tells us that the relative invariant with weight kw means that the number of differentiations invariant, the total number of differentiations is x. Okay, so that's monomial, right? So they can be product of several number of different derivatives, so then sum of those differentiations I see. Okay, so then the weight k, or just omit instead of kw because it's one-dimensional lattice, I just write k. So the weight k of the invariance which is easier is the following: for R3 it's 3, for R4 it's 8, for R6 it's 12, for R7 16, then 20. So you see the 8, 12, 16, 20 is this geometric progression. So 3 doesn't fit into it. So in fact, that's not even a lattice, right? It's just a monoid in a lattice. No, there's no even unity. So it's actual, no, sorry, there is unity because there's absolute invariant, but we consider just additive subset of a lattice. So the W sits into lattice, but it's in general, the realizable weights don't form as a group. Okay, a bit more about this story. It's prolongation of the previous step. So here's the finite generation theorem. This algebra of relative invariance with respect to this six-dimensional algebra is generated by two relative invariants, R3 and R5, and relative invariant derivation. Now see how this invariant derivation looks. That's polynomial actually, not as previous absolute derivations, right? So polynomial, however, it stopped being, actually it's not derivation at all. So because it's actually first order operator. You see first order part, and you see zero order part. Okay, so that's actually first order operator, and it shifts the weight by 4. Relative invariance of weight k go to relative invariance of weight k plus 4, and this k appears in zero order term. Okay, so how do we prove this? We can take this Lie algebra vector fields, we prolong them. We prolong them to force jets. The space of force jets has dimension 6, right? It's x, y0, y1 up to y4. There's 6 coordinates, and there are 6 vector fields. So when we prolong them and put coefficients into matrix, then we can compute determinant. And this determinant tells us precisely when rank drops. That's called Lie determinant, and that's something proportional to y3. So that's actually something proportional to power of y3. That's how we see that y3 is the first invariant. And now when we prolong higher, then the action becomes actually locally free, and there's bijection between absolute and relative invariance. And so we just read off what can stay there in numerator and denominator. And here's the first syzygies, first relation in this algebra. So I take nabla and apply to those R, which I said, and that's quite nice syzygies, complete polynomial relations. Corollary, if you would like to describe ODEs with essential contact symmetries, this means that by no contact conjugation, I can bring this ODE to ODE with only point symmetries. And those ODEs that have essential contact symmetries, they are just few. They actually described completely by elements of this algebra of relative invariance. So we have complete control over all such equations. Okay, for example, there's one ODE of order 3, just triple prime equal to 0, 2 reducible ODEs of order 5, and then actually they are moduli, but they can be effectively described in high order. Okay, now to describe next result, I would like to recall something about homogeneous spaces, even though the result will be more general than just homogeneous. So let's consider homogeneous space G mod H, called M, and let V be representation of isotropy group H of stabilizer. Then we can form homogeneous vector bundle over M is just G cross V over H. This homogeneous bundle E over M has typical fiber V. And particular homogeneous line bundles are classified by one-dimensional representations of H. If you consider generalized Clark varieties, as the case when G is semi-simple and P is parabolic, then the line bundles are parameterized by the lattice. Z, that's another type. I'm sorry, I have to correct it before I send slides. That's not P. P has no center. That's G0 part. So recall that semi-simple Lie algebras have Z gradations, which are up to conjugation in bijective correspondence with parabolics. So I have this gradation of the algebra G, and non-negative part G0 plus G1 plus so forth, that's parabolic. Okay, G0 is reductive, and its center is G0. So this equality is wrong. Actually, it's just G0. So it's reductive. It has semi-simple part plus center. So this is G0, and this is G0 appears in here. Okay, and model tangent space for this homogeneous space M is has natural filtration, and the corresponding gradient is the negative part of this gradation.
So you say that ZP, we should not read it. So only that on G0. Okay.
Ignore the ZP, yes. The ZP actually is 0, yes.
I see.
I'm sorry for this error. Yes, so it's just like reductive with central part denoted by G0, right? That's number, that's rank of ZG0 correspond to number of crosses on Dynkin diagram. That's how we encode the parabolic. Okay, now when I would like to go to curve geometry, right? But I start with model client geometry given by PRGH. And now it corresponds to H principal bundle. So P over M, where fiber is H. Together with affine connection omega on totals, so this is just one form on total space of the bundle with values in Lie algebra G, which satisfies three conditions: H equivariance with respect to structure group H. Then omega shall be isomorphism, so tangent space to P is identified with G, and the vertical action reproduces fundamental vector fields.
Borja, why do you call this an affine connection? It's the Cartan connection, right? Just a one form, G valid one.
Yes, but I mean,
it does not take values on H, right? It's just
affine connection is just what do you say?
I don't know, why do you call this a affine connection? It takes values in G, and the second property is
how it's appeared in Kobayashi Namizu.
Okay, it's called like this.
It's called affine connection in Kobayashi Namizu, but when you put more conditions, right, like that's actually become Cartan connection.
Okay, so it's a valid name. Thank you.
So Cartan connection is a affine connection with all those conditions.
Yes, sure.
Now, parabolic geometry specification of the above in the case when G is semi-simple and P is parabolic. And this is class containing interesting geometries like conformal, projective, Levin degeneracy R, Legendre contacts, and special vector distributions. But for example, it doesn't contain Riemannian matrix. And then you have to consider more general Cartan geometries for those. So the general statement is the following: for parabolic geometries of type GP, the weight lattice for relative differential invariant, that's those realizable for one cohomology of Gelfand-Fuks type, is R in the power rank of Z. Okay, so here have to be G0 again. I forgot to change this error. Okay, so it has to be center of G0. Okay, so and that's basically explained by because P is so we have to look to, let me see, do I explain it on the next page? Actually, I do. So let me show you some diagram which appeared in the context of Cartan bundles related to relativity in a paper with Avi Schneider and David McNaught, but it's like very general picture. So we consider some fine type geometric structures. I call this type Q, metric, connection, distribution, whatever, or maybe we given by equation like Einstein Weil. Let E be bundle of jets of such structures. Okay, and let P be Cartan bundle for a particular such structure. But P, and then pull back of this P to the jet bundle or to the equation of such structures will consist of all possible like Cartan bundles. And then of course infinite jets appears as parametrization for normalizations. Then we get this commutative diagram. Left top corner is just pullback. Now, what the Cartan machinery tells you to do? Cartan machinery tells you to do the following. So you stay here in P, but actually, if you think carefully, you stay here in the left top corner. Because you need to compute not one geometric structure, but actually generic one, so you have jets of it. And then you compute structure functions of absolute parallelism there in P, and the derivative along the frame, because there's, if I said finite type, then actually there's frame, right? So this is algebra of invariant functions here. Okay, and the invariant with respect to G. Therefore, they actually descend down, and they the differential invariants here with respect to G correspond to just those elements from here which are invariant with respect to structure group T. We would like to push them down. In general, these invariants, they stay in the bundle, right? So they defined in the Cartan bundle, and they are not p-invariant. So we take only those which are p-invariant, so they can be pushed down. Now, when we talk about parabolic group, so P structure group becomes parabolic. So it's semi-direct product of G0 and P plus, and P plus is nilpotent. There's nothing one-dimensional which is, there's no, all one-dimensional representation of P plus are trivial. And I talk here about scalar relative invariance, therefore P plus has to act trivial on those. So P plus is gone. Now G0 is direct product of center, well, or maybe almost direct product. That's definitely true for Lie algebra, but maybe slightly not true for Lie group. But okay, let me just say direct product of center and semi-simple part. And again, semi-simple part has no non-trivial one-dimensional representation, so it's gone. So then I actually have to consider just those invariants. They have to be absolute invariant with respect to group H, which is a semi-direct product of semi-simple part and P plus. Okay, but I allow that center X non-trivial on those. Then those will be precisely relative invariants. And this actually explains why the lattice is ZG0. Well, discrete subgroup in ZG0. Okay, let me give you a couple of examples. So one example is very classical. It's maybe the first studied example of infinite pseudogroup in the sense of Lie. That's example coming from Tresse, his dissertation, PhD dissertation of 1896. He actually referred to paper. I have to refer to dissertation. Okay, anyway. So we consider pseudogroup of diffeomorphism of plane R2 with coordinates X and Y. Then we leave this pseudogroup to actions in first jets, second jets, and so forth. It's enough to talk about second jets. In second jets, I consider second order equations given as hypersurface, right? So any second order ODE is given by hypersurface in second jets. There's just a relation between y double prime x, y, and y prime. And I can assume here that y double prime is expressed through the rest. Now I would like to act by point transformation on this. And so this point transformation act on those defining function f. And I would like to see invariance, right? So then I leave to the space of jets of function f, and this produces for me invariance. So then basically there's different jet spaces here, right? So I first start this jet space of map from Rx to Ry, right? And that's just to lift the group to J2 where I see this equation, and then I see how it acts on this function f. That's my new J0 space. It is 4-dimensional. It's mapped from 3-dimensional space with coordinates x, y, p to R, y double prime. And then in this jet space, I do further prolongation. Okay, so there's review of Tresse work in my paper of 2008. Now the lattice of weights here is generated by 1 cocycles, which are precisely those 1 cocycles which you saw in the case of projective action. Okay, so there's one divergence here and there's another divergence here. However, now the algebra is different. Okay, now algebra consists of all vector fields on the plane. Okay, and it's represented in functions. Well, but this functions not now on R2, but this Lie algebra is prolonged, and there will be function on the prolongation space. But still, this doesn't change the statement. There's only two cocycles, two non-trivial cocycles. Now, these are realizable, and for some combination, not precisely for those cocycles, but for their rational combination, their weights, or these are realizable weights. So there's precisely two relative invariants. One which has very simple form is just f fourth derivative by y prime is denoted by p. And the other relative invariance is a bit more complicated. But in fact, there is so-called Cartan duality, or in Lie algebra term, it's auto-involution, auto-automorphism of Lie algebra A2, which is SL3, right? So that's reappearance of SL3 here. That interchanges this invariance. So H becomes simple form, I becomes complicated form. Okay. So maybe one more story is the following. So that's another parabolic geometry is related. So this is parabolic. So this example is parabolic geometry. And that lattice is two-dimensional is in particular case of the theorem I mentioned above. And that's parabolic geometry of the type A2 mod P12. Right, so the second order ODEs are parabolic geometry of the type SL3 mod Borel. Another example of parabolic geometry has type G2 mod P1. G2 is rank 2 exceptional Lie group, and P1 corresponds to first parabolic group. The corresponding gradation of G2 goes from G minus 3 to G plus 3. And the negative part actually has filtration with growth vector 235. That's so-called 235 distribution. Now, as geometry, it is just encoded by undetermined ODEs. Now we consider two functions, y and z dependent on x. And there's one relation between those. There's two functions and one differential equation. And this differential equation is of mixed order. It involves one derivative of y and two derivatives of z. So let's, for example, express first derivative of y through the rest. So then you see there's like 5 variables here, x, y, z, z prime, z triple prime. So this geometry was studied by Cartan in 1910, where he derived invariance. And he obtained from this that maximal symmetry algebra can be G2. And he also gets the first fundamental invariant, so-called Cartan quartic invariant. So that's a polynomial on the rank 2 distribution, these two. Okay, I write it as inhomogeneous polynomial by just, oh no, I write it as homogeneous polynomials. I identify this delta as just two plane with coordinates PQ. And then I write it as homogeneous polynomial. Here it is. It has 5 coefficients, right? So that's irreducible representation of SL2 of type 4 symmetric power of standard representation. Actually, even of GL2, yeah. So GL2 is G0 part of the corresponding gradation of G2. Now, there's two relative invariants here. And they actually, yes, they can be derived from this quartic. So when we see GL2 acting on quartics, there's actually two invariants. So you can take R2 of A, of those coefficients, and R3 of A. And here's expression. One is quadratic, the other is cubic. And actually, this quadratic cubic are precisely to say that the weights of invariants on 2 and 3. So they are proportional, actually, these weights. So in particular, we can take their ratio. Well, if I take the first invariant in power 3 and the second invariant in power 2, and I can take their ratio, I get absolute invariant. So here it is, it's I. That's the first absolute invariant for 2-3-5 distribution in general position. Okay, and this the algebra of invariants, well, can have at most those invariant in denominators. They have order 6 that depends on 6jet of this function f, which we see in here, and but the algebra is very complicated. I will not describe it here. Okay, so to summarize, well, first of all, computation of this Gelfand-Fuks type cohomology is complicated in general. Second, we actually don't need it entire because there may be non-realizable elements, right? So the realizable elements correspond to additive subset of a lattice inside the space of weights. And yes, and that's how things are computed. There are more applications to, for example, Darboux integrability. The test for integrability is expressed through relative invariants, so-called Laplace invariants and their derivatives. The Liouville integrability of geodesic flows, that's what we discussed in the beginning, for example. Yes, that can be also expressed through relative invariants of differential group. When we discuss integrability via geometry, like this dispersional integrability, my collaboration with Eugene Firapontov, David Calderbank, Maciej Dunajski, then there appear also, and Volodya Novikov, then there appear also invariants when we do classification by equivalence group. Yes, even in this general context of like Lux pairs and general covering, as Vinogradov school develops, well, basically this covariance can be reformulated through certain relative invariants because it's usually certain line bundles. And there's also nice recent work. Well, I don't know. So at least in appendix to our recent work with Eivind Schneider on Kund metrics, we explain that this Kund class is obtained from just pure equivalence problem. You consider the action of the group which preserves the shape of the metric on jets of metric, and you look to lower order differential invariants. They actually tells you that that's a Kund class. So they obtained invariantly from this consideration. Okay, so thank you for your attention. That's the end of my talk.
Thank you, Boris, for the very interesting talk. So the others, any question to Boris? If no, then okay, go on.
So let me ask you a question. Integrability via geometry. So such a kind of vanishing of torsion or such a completely integrability. What do you mean?
You first were very good heard, but then again I don't hear you. So
yeah, it's hard to hear. It's true.
But at the beginning it was actually very good.
That's because the audio. Next time I change the path. I understood. I use they choose a different path. Yeah. So can you hear me now?
I try.
Okay, I should speak. So integrability via geometry, that means a kind of the, how to say, torsion of the geometric structure or completely integrability, or what do we mean integrability via geometry?
It means the following. So for usual solitonic types equations, right, there's different approach to integrability. There's Lux pairs and differential operators. There's infinite many symmetries and conservation laws, right? There's recursion operators and the Hamiltonian, bi-Hamiltonian structures, all this type of the story, right? For solitonic type equations. However, for dispersive equation, so usually these things change completely. So for example, Lux pairs becomes not pairs and differential operators, but pairs of vector fields, right? So the recursion operators look different, and there is usually not Hamiltonian structure in the standard form, as you understand, like this Novikov-Dubrovin type brackets and so forth. When you work in solitonic equations, right? So you have to work on infinite dimensional manifold. And that's infinite dimensional Hamiltonian formalism. But for dispersionless equations, actually, you can work on finite dimensional manifolds. And then there is geometric structure which actually are responsible for integrability. Einstein-Weil self-duality structures, these are such. So they actually just finite dimensional things, which gives a usual convenient geometry. That's dispersionless equations. For them, these things are applicable.
Yes, so another question. So that first is like to have your slides. Secondly, reference. You of course you show some your paper. It's Lie-Tresse, it's a Schneider, but there are more or something new or.
Which paper do you mention?
On the reason here, because you mentioned from the beginning, your paper is Lie-Tresse, then the Schneider, then your paper 2008 on the Aben Symposium, yeah.
Integrability via geometry, it's title of my paper with David Calderbank.
Yeah.
Yes, it's with David Calderbank. With Schneider, that's different. That's number 5 actually, right?
Yes. Yes. So on the references in this slide, so how you can find or you have to check. I don't see yours. How to say the reference? Of course, you provide some reference, but everything here in the slide, right?
Excuse me?
The question about references.
No. Okay, no. That's the last slide is not references, but I will add references. I will send updated slides.
Yeah. Thank you very much. Yeah.
I will send updated slides where I correct some errors which I told during the lecture, and also add references.
Yeah, I also correct the title. As the first page, there are invariant and then there are typo.
Yes.
Yeah.
Yeah. Okay.
Okay, maybe I will ask one more question. So I remember there was some general theorem about the lattice of weights, which is finitely generated, right? If I remember correctly.
Yes.
So up to a certain level of jets, then it's the coefficients are absolute invariants, right? So for which kind of pseudo groups it's true? The theorem. Algebraic. So for any, not necessarily transitive or only transitive. How is it?
No, transitive on the base.
Transitive on the base. Okay.
I don't know how to remove this requirement.
So the same as Lie-Tresse for you and for in your paper for this checking. Okay,
absolutely.
Right. I see. Yes. And the second question: what kind of so you enumerated certain things which are already solved, right, by you and collaborators. What kind of open questions here? Because of course there are probably more problems, right? What kind of open questions do you see?
Well, for example, how to extend it to general Cartan geometries? Because I said what is the weight lattice for parabolics, right? But and also what to do with like submanifolds in those geometries.
And for parabolic, where is it written? You will add this reference, right? Just to know.
It's not yet.
Not yet. I see. you will. Okay, I see.
Yes, but
it's done. It's done.
Yes. Now, another open questions would be actually, but it's the even concerns the general theorem with Lie-Tresse. What to do if the action is not transitive on the base? We showed some examples where things getting really complicated when the theorem just fails.
Yes.
But the existence of counterexample doesn't mean that you cannot try to extend this theorem to more general context.
It's usually more complicated, right? So
you just have to do a more complicated theorem. But that's open question. What to do in the intransitive case?
And then the same about weights, right?
And then the same about
yes. I see. And you even don't know whether it's finitely generated in this case, right? Because it's
the conjecture is that yes, it is, and it actually meets very well Arnold conjecture about rationality of Poincare polynomials for jets of geometric structures, because like in the case of GLT, one corollary is actually this Arnold conjecture is true for those classes of pseudo group.
I see.
But Arnold conjecture is more general. It doesn't require that the pseudogroup is
It's
transitive.
transitive.
Actually, that is always true. Like
Was it for pseudogroups or just usual groups? Usually groups.
Pseudogroups.
Pseudogroups.
Pseudogroups, yes.
Okay. Okay, this sounds interesting.
And that's open. Yes. And
Yeah, sure. I understand. Thank you. Okay, if there are no questions, let's thank Boris for the nice talk.
Okay, thanks for your attention. Goodbye.
Bye.